Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's a pleasure to have Ran Raz with us this week from Weizmann, and I don't think I should say much more because you already know him. He's so famous that, you know, the words are unnecessary, so okay, there you go.
Thank you for the introduction and for inviting me to give this talk. Actually, oh, I see, okay. Okay, so thanks for inviting me to give this talk. Actually, I wasn't sure if to give this talk or some other talk about a survey about parallel repetition theorem and applications. Finally, I decided to give this talk. So if you want to hear the other talk, you will have to invite me again. The title of this talk is How to Fool People to work on Circuit Lower Bounds. And I will explain the title in some minutes, but at this point I just want to say, because Dan already said that he's not fooled to work on circuit lower bounds, so I want to say I'm not going to show any lower bounds here, and I'm not going to fool you to work on circuit lower bounds. What I'm going to do is to show you how to fool other people to work on circuit lower bounds. That's why it's very important to come to this talk. So what do I mean by lower bounds? In general, I talk about lower bounds for circuit complexity, but in this particular talk, I'm going to talk about arithmetic circuit complexity. When we talk about arithmetic circuits and formulas, I will tell you what it is. When we talk about arithmetic circuit and formulas, we have some field f that can be any field. Sometimes we talk about C or R, but many times about finite fields. And in this talk, you can take, sometimes I will talk about C, but usually almost everything that I'm going to say will be true over any field. So we have some field F, and we have n input variables x1 to xn. We have the gates plus and product. An arithmetic formula is a directed tree with edges directed from the leaves to the root of the formula. Every leaf of the formula is labeled by either an input variable from x1 to xn or a field element from the field f. So you see 1 or x1, x2, and every other node in the formula is labeled by one of the gates, either plus or product. And you can see that if we do that, every gate in the formula computes a polynomial in the ring f of x1 to xn in the obvious way. So for example, this gate computes the product of x1 and x1, this gate x2 plus 1, and this gate, the final polynomial computed by the formula, which is in this particular case, x1 times x2 plus 1. So this is, in general, the polynomial computed by a formula. When we talk about arithmetic circuits, it's exactly the same. Again, we have the same gates, the same variables, the same field, except that we allow arbitrary directed acyclic graphs rather than trees. So this time, this can be any directed acyclic graph, so which means that we can use a computation that we already done. We can use it more than once. So this is an arithmetic circuit, and again, each gate in the circuit computes a polynomial in f of x1 to xn in the obvious way. And we usually look on two parameters of the circuit and formula that we use: the size of the circuit or formula and the depth of the circuit or formula. In this talk, I will talk mainly about the size, but I will mention the depth in several times. The size is defined to be the number of edges in the circuit or formula, just the size of it as a graph. And the depth is the length of the longest path. When we talk about the depth, there are two versions. Sometimes we talk about the depth when the fan-in of every gate is unbounded, and sometimes we talk about the depth when the fan-in of every gate is 2. The fan-in is the in degree in the graph. Usually when we talk about depth, we mean for gates of fan-in 2, except when we talk about circuit of constant size, and then we refer to gates of unbounded fan-in. I will usually say if I mean to this depth or this depth. If not, you can assume in this talk that constant depth, sorry. Oh, I'm sorry. When we talk about circuits of constant depth, we talk about unbounded fan-in. For now, you can think of the depth as the length of the longest path, where the fan-in of each gate is 2. But I will talk mainly about the size of the circuit and formula. Arithmetic circuits and formulas are the standard model for algebraic computations. So for example, if you want to compute the determinant of a matrix or the permanent of a matrix or the product of two matrices, then the standard model to look at is arithmetic circuits. And sometimes for simplifications, we look on arithmetic formulas. So these are the standard model for arithmetic computations. You want to ask how many operations we need in order to compute the determinant. You need the model to look at is probably arithmetic circuits. And we would like to prove lower bounds for computations. We would like to prove lower bounds for the size of arithmetic circuits and formulas. For example, for the size of an arithmetic circuit for computing the permanent. The Holy Grail of this research area is to prove super-polynomial lower bounds for circuit or formula size. At this point, we are very far from it. For circuits, the only bounds that we know are omega of n times log r, where r is the degree. N times log the degree of the polynomial computed. That's what we can prove. And for formulas, we can prove lower bounds of omega of n squared, but no super polynomial lower bounds, and that's the Holy Grail. Now, for the $1 million question, will it give the result that p is different than np? It won't give this result, because we talk here about arithmetic circuits and not Boolean circuits. It's a little bit different, but it's a result of the same flavor. Actually, it gives a lower bound for computation, except that it's algebraic computation, so you're not going to win the $1 million prize, but it will be very important scientifically. So why super polynomial lower bounds were still not proved? Maybe it's because not enough people are working on it. So some people think these problems are too hard and are not fooled to work on it. So there are also rumors about all kinds of barriers for proving lower bounds, and sometimes partial progress is not very appreciated. And some people think, okay, the problems are not nice mathematically. You have an arithmetic circuit. It can be something very, it can have many forms. There are not enough starting points for working on these problems. So I have a secret plan. So the plan is to fool people to work on circuit lower bounds. So more or less the idea is to come up with a set of problems that are innocent looking. It seems as if they are completely unrelated to circuit lower bounds. And they should be, hopefully they will be clean and simple problems that can be attacked from many different points of view. That seems very nice mathematically. And then if it will be really interesting mathematically, many people will work on it from many different points of view, and maybe we will make some progress. So that's the plan. It's a good plan, right? So. What?
That's the problems you give to your students?
No, I think.
So this problem is as hard as proving circuit lower bounds.
Which problem?
The coming up with.
No. coming up with it is no, but I will show you some problem. So that's what I wanted to say. It's not only a secret plan, it's also my new hobby, to come up with problems that look nice and clean mathematically, and their solution will give strong circuit lower bounds. So this is the plan, and I will tell you today about two results in this direction. One of them, both of them from the last 2 years. One of them is an approach for proving super-polynomial lower bounds for circuits, and the other an approach for proving super-polynomial lower bounds for formulas. And more or less what I will try to do today is to describe the problems plus giving some comments about it. So first I want to start with elusive functions and lower bounds for arithmetic circuits. And this is an approach for proving super-polynomial lower bounds for arithmetic circuits, even exponential lower bounds for arithmetic circuits. So just to see what we're talking about, so I want to define what's a polynomial mapping. A polynomial mapping is just a polynomial mapping. A polynomial mapping from a field to the n to a field to the m. For this part of the talk, I'm going to take the field as C, the complex numbers, although almost everything that I'm going to say is going to be true over any other field. So a polynomial mapping f, which is f1 to fm, from C to the n to C to the m, is just a mapping such that each coordinate of the mapping can be described as a polynomial in n variables. And I'm saying that the polynomial mapping is of degree d if each of these polynomials are of total degree at most d. So this is a polynomial mapping, very simple. And I also need a notion of what it means an explicit polynomial mapping. And for this notion, I use the notion of polynomial definable of Valiant. So anything that is polynomially definable is explicit from my point of view. And in particular, the following will be explicit. If you are able, given a monomial m of the polynomial and an index I of the polynomial that you want to compute, so you get an index I between 1 and m, and you get a polynomial m, then the coefficient of the m is a monomial. The coefficient of the monomial m in the polynomial fi should be computed in polynomial time. That's what I mean by explicit. Actually, the definition is even more general, but in particular, this will be explicit. And the idea is that most of the things that we are able to construct, that we think about, are explicit. And
polynomial time, what's that a polynomial in?
Okay, so that was exactly the next comment. So this is a very important point. The polynomial time is polynomial in the length of what you get. So you get a monomial and you get an index I, and the polynomial time is polynomial in the length of the monomial, the length of the description of the monomial, and the length of the index I. And this is a very important point, that I allow you polynomial time in the length of the index, and so it's polynomial time in log n, in log m, and not in m itself. And this is important because I will work with m that is super polynomial in n. So the polynomial time is in the length of the index. Nevertheless, I think most of the mappings that one consider usually are explicit in this sense of explicitness. So this is what I mean by polynomial mapping, and this is what I mean by explicit. And this is one example for a polynomial mapping. An example that most of you probably saw, the moments curve, and this is a polynomial mapping from C to the m. F of x is mapped to x squared, x cubed to x to the m. This is the moments curve. And there is one basic fact that probably you have all seen, a basic fact in linear algebra, that for any affine subspace F A of dimension m minus 1, any subspace of C to the m of dimension m minus 1, the image of F is not contained in the subspace A, in the affine subspace A. This is very easy to prove and very basic. I can write it equivalently as follows. For any polynomial mapping gamma from C to the m minus 1 to C to the m of total degree 1, so gamma is just an affine mapping. For any affine mapping from C to the m minus 1 to C to the m, the image of F is not contained in the image of gamma. And this is because the image of gamma is an affine subspace, and any affine subspace can be written as the image of some affine gamma from C to the m minus 1 to C to the m. So we have this property that the image of F is not contained in the image of gamma for any mapping of total degree 1. That's the property that we have. And what I'm asking is what happens if we consider mappings of total degree 2. And what I would like to get is an explicit example for a polynomial mapping from C to the m, such that for any mapping from C to the m minus 1 to C to the m of degree 2, the image of F will not be contained in the image of gamma. That's what I want. And I allow you to use mappings F of degree almost exponential. 2 to the m to the little o of 1, which means smaller than 2 to the m to the epsilon for any epsilon. So I don't allow you exponential degree, but almost exponential degree. And that's what I'm looking for. Just such a mapping F such that the image of F is not contained in the image of gamma for any gamma of degree 2.
Do you have some lower bound on the degree that's going from necessary?
I think that m squared, more than m squared is probably, more than m squared you can probably do that. And less than m squared, probably not.
I mean, less than m squared.
Less than m squared probably you cannot do, and more than m squared, a little bit more than m squared you can do that. So I can prove it non-explicitly that more than m squared you have such a mapping. But here I'm asking if there exists an explicit mapping, and that's the problem. And if you find such a mapping, you prove exponential lower bounds for computing, actually super-polynomial lower bounds for computing the permanent over C. So
why is it important that it should be explicit?
Okay, so if the mapping is not explicit, you still get a lower bound, but for a non-explicit function. And we know lower bounds for non-explicit polynomials by counting arguments. Actually, here it's dimension arguments, not counting, because the field is C. So this is not very hard to do. If you want it to be true for explicit polynomials, you need to give an explicit mapping, and then it follows that it's also true for the permanent. So this is what I'm looking for. And you can see that this problem seems very innocent. It seems unrelated to complexity or to arithmetic circuit complexity. It seems that one can try to study it for many different point of views, maybe from a geometrical approach, algebraic approach.
And the moment map is not such a function?
The moments, no, it's not such a function. It can actually be, the image is contained in the image of gamma of degree 2 and the square root of m variables. So it's not such a function. I can give you many examples for such functions, but I cannot prove it for any of them. So
Give me an example of what?
for such functions, but I cannot really prove for many candidates. But I don't want to get into it. Almost everything you think about will be a good candidate, because that's how it is. That's how it is in this research area. It's hard to prove the lower bound. So you can, for example, the permanent is a hard candidate for arithmetic circuits, but you cannot prove it. I cannot prove it, at least.
If, by the way, if you find something that has a degree much smaller than 2 to the m to the o,
Okay,
to the
so
that give better bounds?
Yes. So this, if this is the degree, you get a super polynomial lower bound. If the degree is much smaller than this, you get a better lower bound up to exponential lower bound. You can get really strong lower bounds by this approach if you only find such a function. Another comment is that the problem is even easier. Gamma doesn't need to really depend on m-1 variables. It shouldn't really be of dimension m-1. It can be of dimension m to the 0.9. And f can depend on n variables where n is m to the little o of 1. And this will still give what I need. And if you, so again, this problem seems really unrelated to complexity. I didn't mention here the word complexity. I said explicit, but that's the only thing that I said that is somehow related to complexity. And in this word explicit, this word hides all the complexity of the word complexity. So this is the first problem that I wanted to talk about. Actually, I can generalize it and define an elusive function. I want to say that f from c to the n to c to the m is SR elusive if for any gamma from c to the s to c to the m of degree r, the image of f is not contained in the image of gamma. And I can show for many settings of the parameters that explicit construction of elusive functions imply lower bounds for the size of arithmetic circuits. So in general, elusive functions are very related to lower bounds for arithmetic circuits. Okay, I'm not going to really give the proof, just the proof idea. Actually, the idea is kind of simple, and I just want to give the proof idea. So what we consider is a mapping gamma from C to the S to C to the M that maps a circuit, a description of a circuit, to the polynomial that is computed by the circuit. And if we have such a mapping gamma, the image of gamma is just the set of all polynomials that can be computed by small circuits. And the trick is to show that this gamma can be taken as a mapping of small degree. Actually, this is not exact. The image of gamma will be embedded in the image, will be contained in the image of a mapping of small degree, sometimes even degree 2, depending exactly how we work. So when we have such gamma, the whole business of proving lower bounds become just is reduced to the problem of finding points outside the image of gamma. Now, suppose that we have an elusive function f. We have a function f such that the image of f is not contained in the image of gamma. Then f hits a hard polynomial because it hits a polynomial that is not in the image of gamma. And the last point is that we take that polynomial f and we add these variables as we take the variables that are needed to describe f and we add them as additional variables to the polynomials here. I mean that in the image of f there is a point that corresponds to a polynomial that is hard to compute. So this is, that's it. I'm not going to really, I don't really want to do the proof or talk more about it. It's just the proof idea. and this is what gives the result. Now you can ask how to get the result for the permanent, and the result for the permanent you get just by Valiant's theorem that the permanent is a complete function for VNP, for Valiant arithmetic version of NP. So if you get a lower bound for any explicit polynomial, you also get a lower bound for the permanent. So that's more or less in one slide, that's the proof.
If you're using Valiant's theorem, is there an explicit proof of Valiant's theorem without randomness?
Yeah, there is an explicit proof. What do you mean?
So have some mistakes. Okay, maybe I'll
Okay. I just want to mention that there is one class of circuits for which the best known lower bounds are proved by this approach. And this is lower bounds for depth D, for constant depth arithmetic circuits. Unlike Boolean circuits, I guess many of you know that for Boolean circuits, we are able to prove exponential lower bounds. For arithmetic circuits, this is not the case. The best lower bounds that we know for arithmetic circuits are size lower bounds of n to the 1 plus omega of 1 over d, and this is for circuits of depth d. And the proof for this lower bound use exactly this approach of elusive function. This was implicit in the work of Shoup and Smolensky in 91 and was made explicit in my work. Okay, so what I want to talk now is about another approach in this direction. And this is a work from actually last year, from half a year ago. Tensor-Rank and lower bound for arithmetic formulas. So let me tell you what is Tensor-Rank. First, what is a tensor? By n, with this parenthesis, I denote the numbers 1 to n. And here n and r are two integers. R is the dimension. A tensor is just a function from n to the r to f, where f is some field. So this is a tensor of dimension r, exactly like matrices, where r equals 2, it's a matrix, where r is larger, it's a tensor. We say that a tensor A from n to the r to f is of rank 1 if it can be written as a product of vectors, exactly like in matrices of rank 1. So A is of rank 1 if there exist r vectors, a1 to ar, from 1 to n to f, so vectors with n coordinates, such that A is the tensor product of these r vectors. A is a1, tensor product a2 to ar. Or more formally, if the entry I1 to IR of the tensor A is just A1 of I1 times A2 of I2 times AR of IR. So this is a tensor of rank 1, of tensor rank 1. In general, we define the rank of A as the minimal k such that we can write A as the sum of k tensors of rank 1. And this is exactly a generalization of matrix rank, except that we talk about tensors of higher dimension. For any tensor A, the rank of A is at most n to the r minus 1, exactly like the rank of a matrix is at most n. So this we know. So everything here is just a generalization of matrix rank. Given a tensor A from n to the r to f, and nr variables, input variables, x11 to xrn, I can think of these nr variables as partitioned into r sets of n variables in each, and define a polynomial fa in these nr variables that corresponds to the tensor A as follows. So the polynomial fa, in the polynomial fa, I take every multilinear monomial that contains exactly one variable in which of the R sets, and each of these monomials I take with the corresponding coefficient, with the coefficient which is the corresponding element of the vector. So this is the definition. Actually, it's not really important what is the definition. I just gave the definition, but I will only need to know that there is a polynomial fa that corresponds to the tensor A. I will not really give the proofs in this talk. So I will only state the results, and to state the results, it's only important to know that for a tensor A, I can define a polynomial fa, and it's not really important for the rest of the talk what is exactly the definition of this polynomial fa. But if you want, this is the definition. So given a tensor A, we have a polynomial fa that is defined as follows, and it is very well known that there is a connection between tensor-rank and lower bounds for arithmetic circuits. And this connection goes back to Strassen, a work of Strassen from 1973. And what Strassen showed is that given a tensor A of dimension 3, A from n to the 3 to f, the rank of M is a lower bound for the arithmetic circuit complexity of the polynomial fa. So if, in particular, if you are able to give an explicit tensor A from n cubed to f of rank M, then you get an explicit lower bound for, then you get a lower bound of omega of M for an explicit polynomial f of A. So this was observed by Strassen. Actually, this is practically an observation. It's just to notice that you can, given some known results, this is practically an observation. When you use this, you can potentially prove lower bounds of up to omega n square for arithmetic circuits, because such a tensor can be of rank omega of n square. But at this point, we still don't know any tensor, any explicit example for a tensor of rank larger than omega of n. So this approach doesn't give any bound better than omega of n, and actually no other approach gives any bound better than omega of n for polynomials of degree 3. In this particular case, fa is a polynomial of degree 3. But potentially we can get lower bounds of omega of n square by this approach. And what I tried to do is to consider tensors of larger dimension. And what I consider are tensors of dimension r, which is super constant. Think of r as any super constant, any number larger than any constant, and smaller than log n over log n. And what I can prove, that if you have a tensor A from n to the r to f of rank n to the r minus, n to the r times 1 minus little of 1. So what you need is a tensor A of dimension r such that the rank of A is larger than n to the r times 1 minus epsilon for any epsilon. So it should be larger than n to the 0.99 r. And the same for any constant smaller than 1. That's what you need. You need a tensor with tensor rank close to n to the r, in the sense that it's larger than n to the r times 1 minus epsilon for any epsilon. And if you get such a tensor, if you get an explicit example for such a tensor A, this gives you super polynomial lower bounds for arithmetic formulas this time for the polynomial fa. And again, the lower bound can also be proved for the permanent. If you get an explicit example for such a tensor with high tensor rank, you prove super polynomial lower bound for computing for arithmetic formulas for the permanent. So it doesn't give you for the more general notion of arithmetic circuits, but it does give you for arithmetic formulas. So this is the approach, more or less.
What is not for random tensors?
So again, for random tensors, the rank is very close to n to the r minus 1. Also in the previous approach, it's I want an explicit one that you can describe. Again, the notion of explicit is exactly the same as before. If I give you the index of an element of the tensor, I want you to be able in polynomial time to output the...
When you give me the index, then I'll randomize.
Actually, in this particular case, even polynomial time in n would be fine, would be enough. Also, in the approach of elusive function, it's very easy to do it non-explicitly, to show that some random construction works. But here also, to get if you take some random tensor, you know that its rank is high. But you need it for an explicit example. That's the name of the game here. But if you do give such an example, you get super-polynomial lower bounds for computing the permanent. So again, in order to prove lower bounds for the permanent, you just need to give one example for a tensor with high rank. That's all you need. Again, it's a problem that seems unrelated to computational complexity, but if you solve it, you prove an extremely strong and important result in arithmetic circuit complexity.
All the computational complexity is implicit in the word explicit.
Here, not so much, yeah, but yes, in general, yeah. So, in order to satisfy Yuval, now I will give a problem that doesn't use the word explicit. Oh, not now. It's in the next slide. Okay. Before I'm going to satisfy, before I'm going to do that, I want to highlight one aspect of this result, and this is the point of view of depth 3 versus general arithmetic formulas. Here, when I talk about depth 3 formulas, I talk about formulas with unbounded fan-in for every gate. And it's not hard to see that tensor rank correspond in some way to depth 3 formulas for the polynomial fa. Actually, set multilinear formulas, but I don't want to get into it now, what it is set multilinear exactly. But anyway, if you have a description of A with small tensor rank, you get small arithmetic formulas of depth 3 for the polynomial fa. And this means that if you prove strong enough lower bounds for depth 3 arithmetic formulas, you get super-polynomial lower bounds for general arithmetic formulas. But the strong enough needs to be very strong. You need to prove a lower bound of close to n to the r for arithmetic formulas of depth 3. But if you do that...
The sum of a product of a bunch of inner products?
Yes. Sum of products sum of products of sums. Exactly. Usually we don't count the product with a constant as part of the depth. That's the... Okay, so I should say that. So it was a folklore theorem that if we prove strong enough lower bounds for depth 4 circuits, arithmetic circuits, we get exponential lower bounds for general arithmetic circuits. And also a recent result by Agraval and Vinay show that any exponential lower bound for depth 4 circuit implies exponential lower bound for general circuit. So this result is that only very strong exponential lower bound for depth 4 circuit implies such a bound. And this result is that any, even a relatively weak exponential lower bound for depth 4 circuit implies exponential lower bound for general arithmetic circuit.
Same.
What?
The same Vinay, right? From HP. The other car Vinay.
The infamous one.
I don't know actually.
Is it?
find that?
I don't know.
What?
Famous.
Infamous sounds more interesting.
Okay, so now I want to talk about an approach of how to construct tensor with high tensor rank. And again, this approach goes back to Strassen. And the idea is the following. Suppose that you have two tensors, A1 and A2. A1 is a tensor from N1 to the R to F, and A2 from N2 to the R to F. And you take the tensor product of A1 and A2. And this is a tensor from N1 times N2 to the R to F. And the tensor product, this is what I mean by tensor product. So A of, now the R indices of A are in N1 times N2, so I can think of each of them as a pair I1 and J1 in I1 in N1 and J1 in N2. So A of I1, J1, I2, J2 to IR, JR is just A1 of I1, I2 to IR times A2, J1, J2 to JR. So this is the tensor product of two tensors. Now, for dimension 2, for matrices, we know that the rank of the tensor product is the product of the ranks. This is well known. For dimension R, larger than 2, this is not true in general. But the question is whether we can prove that it's approximately true, that the rank of the tensor product is larger than the rank of A1 times the rank of A2 times something, time 2, time 100, or maybe even times, divided in 100, or maybe divided by n to the little o of 1 even. If you prove such a thing, you get super-polynomial lower bounds for arithmetic circuits for the permanent.
For formulas or for
Formulas, sorry. Thank you.
Do you need to prove this? Do you have to prove it for R equals 3, or do you need to prove it for...
So you need to prove it for, if you want super-polynomial lower bounds, you need to prove it for R that is super constant. For any R that is super constant and smaller than log n over log n.
If you prove it for 3, you already get some...
So depending what exactly you prove, but you can get, if you prove something very strong for 3, you already get very strong lower bounds, but polynomial, like omega of up to n square. So even for 3, it's extremely interesting. But for R, you can, for R larger than 3, you can even allow larger losses.
So are you going to talk about what's known about how much less? How much less can rank in A?
So actually, I'm not sure exactly, but very little less. There are examples in which it's less than the product of the ranks, but very little. Maybe a constant or something like that. Maybe even less than a constant. I'm not sure what are the best examples. So the proof for that is very easy. I'm going to do it fast because it's less important. So if we have such a theorem, what we're going to do is to take M to be n to the 1 over R. And then suppose that we have R tensors A1 to AR from M to the R to F of high rank, of high tensor rank. We're just going to take the tensor product of these R tensors. And this is a tensor from N to the R to F. And if all of these are of high rank, then this will also be of sufficiently high rank. Now, of course, you can ask, where do we get A1 to AR from? So the idea is that since M is n to the 1 over R, each of these tensors depend on only n coefficients. And therefore, you can fix these coefficients as additional input variables for your formula, as kind of auxiliary input variables. And since the tensor rank of a random vector is high, you will get that this will be in general of high rank. So that's more or less how you get the proof. So you can see this problem. this problem doesn't mention at all the word complexity. I can even write here 1 million, so you will not even have little of 1. So it doesn't mention complexity. It's a problem in algebra. If the people in algebra were more serious, they would have solved it a long time ago. So, and if you prove it, you get super-polynomial lower bounds for computing the permanent by arithmetic formulas.
Well, the question is whether rank is actually an algebraic object.
What?
I think the algebraists, I can't speak for them, but might respond that rank is not really such an algebraic object.
Okay. So we will have to prove it ourselves. Okay. I'm not going to do the proof. The proof in this case is a little bit more complicated. I'm going to describe the main steps of the proof, although I know that in this forum you will not get much out of it, but it's only one slide, so it's okay. So suppose that we have a small formula for FA. How do we get from it? We want to prove that the tensor rank of A is small. So the first step is to put the formula in some nice form. We need to homogenize the formula and make it homogeneous and multilinear. And I will talk a little bit about this step later on. Then when the formula is in a nice form, I define a notion of syntactic rank of a formula. And this notion, unlike tensor rank, you can just go over the formula and compute the syntactic rank exactly. Tensor rank is hard to compute. If you get a tensor, it's actually NP hard to figure out what's the exact tensor rank. This is a result by Johan Astad. And this is even for tensors of dimension 3. But the syntactic rank can be very easily computed by going by looking at the formula. And once we have this notion, and this notion will bound the tensor rank from above, we can actually, for any formula, compute its syntactic rank, and we can actually find the formula with the highest syntactic rank. And this way, we will bound the tensor rank. So I know that this is not really a proof. It's just the steps that need to be done. But I just want to talk a little bit more about the first step of the proof, because this might be interesting in its own right, although it's not really, it's less related to proving lower bounds. So the problem here is the problem of homogenization. So first, what's a homogeneous polynomial? A homogeneous polynomial is a polynomial such that all the monomials that appear in the polynomial are of the exact same degree. That's a homogeneous polynomial. A homogeneous formula is a formula that, such that in every intermediate stage computes a homogeneous polynomial. So all the gates compute homogeneous polynomials. In general, if you want to compute a homogeneous polynomial f, you can compute it by a non-homogeneous formula. Maybe the formula computes in intermediate steps some other polynomials that are not homogeneous, but finally it all cancels and the final output is homogeneous. Now suppose that you have a formula C of size S that computes a polynomial f, which is homogeneous and of degree r, but you don't know that the formula is homogeneous. Can you construct from it, can you construct from it a homogeneous formula D for the polynomial f? And this question again goes back to Strassen in 73, and Strassen gave a very simple, kind of the obvious procedure to construct D from C. But the problem is that D is of size S to the O of log R, where R is the degree. So it's a very efficient procedure when you look on the circuits. But if you look on formula size, it increases the formula size. If R is more than a constant, it increases it blows up the formula size super polynomially. And this procedure was actually conjectured to be optimal by several people. And the first step of what I described is actually a different analysis of the same procedure that shows that actually D can be taken of size D plus R, choose R times S. Here D is the product depth of the formula C when the fanning of every gate is D, and R is the degree. It's not really important what is exactly this expression. The important thing is that this is always smaller than this. This is always smaller than this. And when S is polynomial and R is less than log n, you can, without loss of generality, assume that D is less than log n and get that the size of D is polynomial. So if you have a homogeneous polynomial of degree log n, and you have any formula for it of size S, you can, from this formula, get a homogeneous formula for the same polynomial. So this is kind of a new homogenization procedure. And as a corollary of this step, what you can get is that if you prove super-polynomial lower bounds for homogeneous formulas for degree up to log n over log n, actually for homogeneous over up to log n, you get super-polynomial lower bounds for general formulas. And the same can be proved also for what I called set multilinear formulas. I will not tell you what are set multilinear formulas, only what are multilinear formulas. So, so multilinear formulas, it's obvious. A multilinear polynomial is a polynomial such that in each monomial, each variable appears with degree at most 1, either 0 or 1, but not with degree 2. A multilinear formula is a formula such that in any step it computes a multilinear polynomial. So, for example, the determinant is a multilinear polynomial, right? If you want to compute the determinant, maybe by a formula, sometimes some formulas for computing the determinant are not multilinear. So they compute in intermediate stages polynomials that are not multilinear, and somehow at the end all the monomials that are not multilinear cancel. We say that the formula is multilinear if it computes a multilinear polynomial in every stage of the computation, in intermediate stages. So every gate of the formula computes a multilinear polynomial. And today we know how to prove super-polynomial lower bounds for multilinear formulas, for the determinant and the permanent. So we know that any multilinear formula for the determinant or for the permanent is of super-polynomial size. So if you want to compute the determinant by a formula such that all intermediate computations will compute multilinear polynomials, you need super-polynomial size. We know how to prove that. So we are able to get super-polynomial lower bounds for general for multilinear formulas, but unfortunately only for polynomials of degree larger than log n. And in order to get super-polynomial lower bounds for general formulas, by this theorem, we need to get super-polynomial lower bounds for multilinear formulas for polynomials of degree up to log n. So somehow it didn't work this way. Thank you. Even slightly less than log n. No, actually log n. So log n over log n is actually for, oh no, you're right, log n over log n, sure, yeah. So we need to prove it for log n over log n.
More questions?
Didn't Strassen give a talk in the 70s on how to get people to work on tensor ranks?
Well, you got me. So I just want to mention that although it might seem as the new problem is harder than the old one, it's not necessarily the case. I mean, it might be that you can prove that you can prove a lower bound of n to the r minus 2, for example. So it will solve this problem, but it won't solve this problem. So it might be that this problem is easier even.
Got another question too. So what, do people try to introduce other things, other gates like maths, things like that?
So then you don't, you compute other objects, not only polynomials. Yeah, there are work with other computational models, like the Schum-Smell model, and there are other computational models. So this is only for the arithmetic circuit model.
Were you present in Hastad recently gave a survey about this topic?
Where?
I don't remember where, but so we were there, and at the end of this survey of hard problems, Impagliazzo asked him. Anyway, Impagliazzo asked him, are there any problems in this area that haven't been solved, not because they're so hard, but because they haven't been noticed?
Was it in Beijing? I think in Beijing, yeah. I heard about it actually, because a student of mine.
And you know what he answered?
The answer that he would have solved it otherwise.
If he knew set problems, he would have solved them already.
Well, certainly it makes all the problems harder if they were not solved by Hastad, but I wouldn't say that they are impossible. So I don't know. This if you ask me, I was very excited about the elusive function approach and tried to work hard on it, but at this point I'm more discouraged than before, but I'm still very optimistic about the tensor-rank approach. So, but the idea is to fool some, not you, but some other people to work on it.
Who fooled you to work?
Well, he's going to pay for that.
Thanks a lot.
Thank you.